Good morning, everyone. So in today's class, we shall review the idea related to SSA form, which we discussed in the last class, and then we move on to the next topic on regional optimizations. How we do common sub-expression elimination at a region level, at a level or at a scope beyond the basic block level. To recap the discussion from the last class, if you consider the code that is there, which is labeled as original code here, so there is a computation of x plus y on this line, and there is another computation here, and we can easily see that the value computed on the first line can be used in the third statement. Instead of recomputing x plus y again, we can reuse the value that is being computed in the first line. But the problem though is the computed value is destroyed by the definition to the variable in the second line. So this is a problematic definition. And this definition is preventing us from using the value that is computed in the first line and stored in the variable a in the third line. But if we convert this code into static single assignment form, then every definition of a variable, it creates a new version of the variable. So here we say these assignment statements, we call them as definition points. So overall, there are 3 definition points here. Out of these 3 definition points, 2 definition points are associated with variable A. And the first definition point associated with variable A, it creates a version of the variable A0. And the second definition point creates a new version of the variable, which is A1. And then similarly, we associated with the first definition point for the variable C, we have this version of the variable C, that is C0. And what we do is, once we transform the code into SSA form, we can apply optimizations on the new SSA form. And we can also see that it is relatively easy to map, to move between, to know, like for example, A0 and A1 corresponds to the variable A in the original program. That's an easy association. We don't need to do any hard work for it. And this is important because when we try to debug code, so the user doesn't know about these variables A0 and A1. When he tries to look at the program, he looks at the program in terms of the variables he has defined, not these underlying variables A0, A1, which the compiler has introduced. But it is not a big deal because we can easily associate these different versions of the variable to the original variable from which they are derived. And if you, again, just to recall, when we are applying value numbering at the basic block level, we use 3 data structures. And I want to recall these data structures once because we will be using these data structures again in the later part of today's class. So we will go through this example just to recap. We maintain 3 data structures. One is variable to value number map. This is one data structure. Variable to value number map. The other data structure is value number to variable map. And the third data structure is a hash table. So in this example, so the compiler starts processing one tuple at a time, and the value number associated with variable x, let's call it as 1. With variable y, let's call it as 2. So here 1 contains x. 2 is the value number 2 is contained in the variable y. And value number 1 plus value number 2, we go and check if it is already computed by looking into the hash table. Hash table is empty. So what do we do? So we say, we make an entry like this. And then we say A0 contains 3, value number 3 is present in A0. This is how these 3 data structures look like after the first tuple is processed. And when the second tuple here is processed, then what we will have is A1 holds value number 4, and 4 is present in value number 4 is present in variable A1. Great. And then when the third tuple is processed here, so the value number associated with x is 1, with the value number associated with y is 1, and that's what we are seeing here. And when we apply an addition operator, so you go and check the hash table, we know that when these two values are added together, the value number 3 will be generated, and value number 3 is present in variable A0. So how do we update this data structure? We update this data structure by saying C0 contains value number 3, and so the value number 3 is present in two variables A0 and C0. And if we do the code transformation, actually the C0 this whole thing will be replaced with A0. That is how we eliminate redundant computations by working on basic blocks which are in the SSA form. So what is the formal definition of SSA form? We say that a program is in SSA form when it meets two constraints. So number one, each definition has a distinct name. So if you look at a program, so let's say there is one definition for variable x somewhere here, and there is another definition for variable x somewhere here. So these are two distinct definition points for the variable x in the program. So, and these two distinct definition points you can easily identify by looking at the program source code. And so this is if there are multiple definition points for a variable, then of course the program is not in the SSA form. So we have to eliminate these multiple definition points. That is number one, in order to convert an IR into SSA form. Second is each use refers to a single definition. So somewhere down the lane, so variable x is occurring on the right hand side. So something like you have a statement like z is equal to x plus y. And there are two definitions which are reaching the use x, In general, the general picture is that this definition could be reaching some set of uses, and this definition could also be using some set of uses. So this is the general picture, and there is this particular use in which these two definitions are intersecting. And a case such as this makes performing many optimizations relatively difficult. So in order to facilitate easy optimization of your program, we want to eliminate occurrences such as this, patterns such as this. So how do we do? So we version these variables. This is definition 1. So let's use instead of x0, let me use x1. So this is definition 1, and this is definition 2. And what do we do? So here, along this path, definition x1 is reaching this use, and along this path, definition x2 is reaching this use. So how do we, and then so there is a conflict because we don't know when we execute the program and when we hit this tuple z is equal to x plus y, whether we will be reaching along this path or along this path. So we don't know whether we should be using x1 or x2. So what we do is we uh, solve this problem by introducing a phi function and a new variable. So we say we introduce a new tuple here, which says x3 is equal to phi of x1 phi of x1 comma x2, and we replace this use of x with x3. So when there are multiple definitions reaching a use, we jam those multiple definitions reaching a particular use by using a phi function and creating a new definition point for the same variable. So the semantics of the phi function is if you reach this instruction, this phi instruction via this path, it returns x1, and if we reach the phi function via this path, then it returns x2. That is the definition of the phi function. So if it's a straight line sequence of code, converting the program IR into SSA form is easy. So you have a sequence of 3 tuples here. So here the original version of the variables, let's call them as x0 and y0. So you are defining the variable a here. Let's call this, this is a definition, one definition point for variable a, and this generates the variable a1. And you can see there is a use, variable a is used in second tuple. So this definition reaches this use. So we replace this use with a1, and there is a new definition for variable a on the second line or in the second instruction. This creates a version of the variable a2. And so here x0 and y0, they remain as it is because they are not defined. And we are defining b for the first time. So we introduce the version of the variable b. So if the code is a straight line sequence of code, translating into SSA form is easy. But if there is a control flow, nonlinear control flow, then it becomes a little bit challenging. Again, we looked at it, this example in the last class. I'll quickly review it. So here we are defining the variable 5. So x1, so we are defining or declaring a new version of the variable that is x1. And this definition is reaching this use. So we replace this use with x1. We are defining the variable x again. So new definition, new variable x2. And this definition is reaching this use. So this is x2. And now we go to this basic block. The definition that is reaching this particular use of x is x2. Along this path, x2 is coming. So we have x2 here. Along this path also x2 is coming. So this use, we replace it with x2. And then we are defining y here for the first time, y1. This definition reaches this use. This is y1. And this is a new definition for the variable y. So we have a new version of the variable y, that is y2. And here w is defined for the first time. So w1 is equal to y1. And along this path, the definition y1 is reaching. Along this path, the definition y2 is reaching. And along this path, the definition x2 is coming down. And along this path, the definition x2 is coming down. So if you see the use of the variable x, the same definition x2 is reaching, whether the control is coming along this path or along this path. So we replace this with x2 and this also with x2. But with respect to y, there is a problem because depending upon which edge the program is using to reach this basic block, we have to use appropriate version of the variable y. So what do we do? So we kind of say y3 is equal to phi of y1 comma y2, and then we will say y3 is equal to this. And here we have w2 because we are defining variable w. It's a different definition point for variable w, and z1 is equal to x2. This one should be y3. So this is how we can take a code which is not in SSA form into SSA form. And wherever multiple definitions are meeting, multiple definitions are reaching a particular use, we are in trouble. So here y1 and y2, they are reaching a use of y. So we want to jam those definitions, and the way we jam those definitions is by introducing this phi function and introducing a new definition variable for y, that is y3. And we use that y3 variable subsequently in the basic block. This is the plan. And so you have to be, so if it is just lack of space, I'm just drawing it here. So let's say if it is a loop, so you have something like x is equal to 1 and x is equal to x plus 1, and based on some condition, you either jump back or you exit. So how do you translate this code into SSA form? So to start with, what we can do is, let me draw this here below so that it will be easy. So here we can say x1 is equal to 1. And then we can say this x2 is equal to x plus 1, and then we come out, exit. And then there's a control flow going back here. And what you can see is along this path, the definition x1 is reaching, and along the back edge, the definition x2 is reaching, and we have a use of x. So the use can be either x1 or x2. So how do we solve this problem? We say x3 is equal to phi of x1 comma x2, and we use x3 here. So this is how we can handle loops. So if you remember these two examples, how to handle loops and how to handle if then else statements, then you have a good intuition about how to translate code into SSA form. There are elaborate algorithms for generating SSA form IR by using some dominator trees, etc. In this course, we will not look at those algorithms. But I want you to be aware that at some point when you encounter this problem of translating a regular IR into SSA form, there are excellent research papers, and there is a lot of work that has been done in this space. You can refer to those research papers. But otherwise, for the sake of this class, this intuition is enough for us to move on. The next idea is, we know that SSA is, so there is no such thing as a phi function in any of the target machine architectures, right? So after we perform all the optimizations on the program, which is in SSA form, we want to translate it into out of SSA form, or rather what we would like to do is, rather than saying that we would like to translate it into out of SSA form, we need to find a mechanism to eliminate these phi functions. That's what we are looking for. because they don't have any equivalent physical realization in processors. So if you see the code here, so this is an interesting piece of code because it is able to generate a control flow graph with a where a particular basic block has more than two predecessors. Usually, if you just use simple if then else statement, it has usually the control flow graph, the basic block will have only two predecessors, but here is a piece of code where the basic block, which is encapsulating this printf statement, it has more than two predecessors. So you can reach this printf statement after executing this statement, max is equal to a. So that means you are taking this particular path to reach this printf statement, or you can reach the printf statement via this path, that is by setting max is equal to c. So in which case you will be taking this particular path to reach the basic block containing the printf statement. Or you can reach this after executing the statement max is equal to b or max is equal to c. So overall, you can see the resulting control flow graph looks like this. And you can see there are 4 definition points for the variable max. So this is the first definition point which generates max1 variable. This is the second definition point which generates the max2 variable. This is the third definition point. This is the fourth definition point. And each of these definition points, they generate different versions of the max variable. And so and all these max1, max2, max3, max4, all these different variables, these definitions reach the same use. So we jam those multiple reaching definitions by introducing a phi function and by creating a new variable max5. So this is a program in SSA form. So you do all optimizations here, and in order to translate this code out into SSA form, one approach is, in the preceding, in the predecessor basic blocks, at the end of the predecessor basic blocks, so you introduce a temporary variable t, and you say t is equal to max1, t is equal to max2, so on and so forth, and now we say max5 is equal to t. So actually, after translating this out into SSA form, you can do a minor copy propagation within a basic block, and we can translate the t is equal to max1 to t is equal to a statement. It's possible. Okay, that's a different thing though. So, but we can do that. So if you leave that aside, so this is one particular approach for eliminating phi functions in the SSA. So in this example, we introduced a new temporary variable. In this particular example, where x0 is reaching along this path and x1 is reaching along this path, and we are merging those definitions by introducing this particular phi function. And the way we can eliminate the phi function again here is, instead of using a temporary, we can just say x2 is equal to x0 and x2 is equal to x1. And yeah, so this is one particular way of eliminating the phi functions. This looks slightly better than the previous approach, except that it seems it may cause problems when there are in certain cases. So in that respect, in the last class, we have seen how when we start with this SSA form representation, the one which you are seeing on the rightmost, where we are using temporary variables, is the correct translation. But if you try to avoid using temporary variables and optimize on that, you will end up doing a translation which is incorrect. But I'm not quite convinced about this example. So this is where I got stuck just before I came to this class, came to this session. Maybe I will post a clarification message on this later. But for the time being, all I want you to appreciate is this could be a minor thing or a major thing if you're actually implementing, if you're actually working with SSA IR in terms of translating SSA IR in, so that you can generate machine code. This could be an important thing, but for the time being, this nuance shouldn't worry us, yeah, quite much. So all I want you to understand is you start with a code and you translate it into SSA form, perform optimizations in SSA form. And after that, we have to eliminate fee functions because there is no physical realization of fee functions in the target processors. And there are approaches to eliminate fee functions, like we have seen two approaches. One is by making use of a temporary variable. The other is without using a temporary variable also you can do it, but you have to be careful when we are doing these things. That's all I want you to keep in mind. Now let's move on and look at what are called as regional optimizations. So the value numbering technique that we have seen before, it works at a basic block level, but we want to, but if you just work at a basic block level, we may lose out on optimization opportunities. For example, in this case, you can see, so we are computing A plus B here. We are computing A plus B here. And if you apply just local value numbering, this second redundant computation A plus B will be eliminated. But then, so this is the computation, and this is another computation of A plus B. This is another computation. So this is also another computation, and this is all A plus B and A plus B. You can see that overall 1, 2, 3, 4, 5, 6 computations of A plus B are there, and except for the first one, we can say the other computations are all redundant. But since we are working only at the basic block level, these only we are able to eliminate this redundant computation, and we are not able to eliminate the rest of the 4 redundant computations. Similarly, the case with the computation C plus D. If you look at the computation C plus D, so you are computing C plus D here, 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 C plus D here. So here we cannot eliminate all the computations of C plus D, but if the program takes this particular path, let's say when the program executes, if it takes this particular path, then definitely we can say this redundant computation and this computation, we can eliminate them. And if the program takes this path, then we have to compute this C plus D. This we cannot eliminate because along this path we are computing C plus D for the first time. So, but after this computation, we can eliminate this computation, we can eliminate this computation, and we can eliminate this computation. So the important observation here is in the case of A plus B, the first computation is a compulsory computation. The computation that we have here, this is a compulsory computation. The rest are all not. They are not compulsory computations. We can eliminate those redundant computations. But when it comes to the expression C plus D, so this is a compulsory computation. And this is also a compulsory computation. And the rest of all the computations of C plus D, we can eliminate. But in order to eliminate them, we should consider a scope which is beyond a basic block level. So in this context, so we define what is called as an extended basic block. So what is an extended basic block? An extended basic block, what we do is we take this control flow graph that we have here and partition it into extended basic blocks. So an extended basic block, it consists of a leader, and a leader can have multiple predecessors. More than one predecessor a leader can have, and the rest of the basic blocks in the extended basic block, they have only one predecessor. So here we start with the root, the first basic block A here, and so we include B in it because B has only one predecessor, and we include C in it. So C also has only one predecessor. Similarly, we include D, we include E, and we cannot include F because F has two predecessors, one is D and other is E. So we stop here. So this is extended basic block 1. What is extended basic block 2? So we take a basic block which is not present in the first extended basic block, that is F. And we see if we can, so if you see F is a leader for this extended basic block, it has two predecessors, it is all right. But can we include G in extended basic block 2? No, it's not possible, because if we include G and G has two predecessors, so we cannot have a, we cannot include G in the extended basic block. So we go to extended basic block 3, and the only basic block that is left out is G. So we have G, and this forms the third extended basic block. So we take the control flow graph and we divide the control flow graph into a collection of extended basic blocks. All right. The important idea here is if you take an extended basic block, each extended basic block is like a tree. Each extended basic block is like a tree. So here extended basic block 1, if you see its representation, it is like A, B, C, D, E. So an extended basic block is like a tree, and the root of the extended basic block, it can have multiple predecessors, it is all right. But the rest of the basic blocks within that extended basic block, they should have only one predecessor. So here if you see, F is the extended basic block. So it is a tree with only one node, which is the root. And we know that F has two predecessors, but these two predecessors they are from a different basic blocks. This is EBB2. So similarly, EBB3 is G. It is the root and it is the only basic block, but it has two predecessors, and these predecessors are not from within that EBB, but they are coming from outside. And the key idea here in super value local numbering is when you are working at B, when you are trying to eliminate redundant computations in B, you can use the computations that are done in its parent node A. The same is the case here when you are working with the basic block C. You can use the redundant computations from basic block A. You can use them to eliminate redundant computations in C. Similarly, when you are working with C, you can use the redundant computations from its ancestors, just not from C, but from C and A. You can the computations that are done in the basic block C and A, you can use them in D, and so is the case with E. And this is the key idea behind super value local numbering. So, and this is an example of what is called as a regional optimization, where we work beyond a basic block, but not at the whole control flow graph level. And the important thing here is when you are working with this super value local numbering, etc., in order for these things to be effective, the IR better be in SSA form. So let's look at this example. and see how the super value local numbering algorithm works. So here, so when we are working with, let's say, we start with, what we do is we do local value numbering at an extended basic block level. So here, so first we consider, sorry. So we consider the basic blocks E, B, C, D, E together once, because this whole thing belongs to one extended basic block. And let's see how this works. So we start with basic block A, and recall we have three data structures. One is var to value number map, and other is value number to var map, and other is the hash table. So these are the three data structures that we have. So when we are working here, so if you do the value numbering algorithm, so you say variable A naught contains value number 1, variable B naught contains value number 2. So 1 is present in A naught, 2 is present in B naught. This is 3. So right. So like that you, and then similarly you go and process the next tuple. This is 1, this is 2, and the value number associated with this is 3. So let me write it down. N naught contains 3. And since due to lack of space, I'll just write 3 is present in N naught also. Otherwise, you can just merge them into one linked list. And this is the state of the data structure. This is the state of the data structure when you process the basic block A. And when we go and process basic block C, what happens is we don't start with a clean slate. So what we do is we use the data structure that we have created for A. So what we do here is, let's say when we are processing this whole thing is for A. So when we are working with C, you look at C has its own variable to value number, VN to var, and the hash table. It has its own data structure. But what is important is, it considers the data structure that is created by A as its parent. So what it does is, when it looks at A naught, it goes and looks at its own table. A naught is not present in its own table. So it goes to its parent data structure. And from the parent data structure, it knows that the value number associated with A naught is 1. The same thing happens for B naught. From the parent data structure, it concludes A naught contains, B naught contains the value number 2. And then, so 1 plus 2, value number 1 plus value number 2, it generates the value number 3. It concludes it by looking at its parent data structure. And then, and then it also knows that value number 3 is present in either the variable, it is present in both the variables M naught and N naught. So it can replace this computation A naught plus B naught with M naught. But there is one thing it does here within its local data structure, that is within its local data structure, it says Q naught contains the value number 3, and value number 3 is present in Q naught, and its hash table entry is not going to change. So this is the state after the state of its local data structure after the first tuple is processed. But when it comes to the second tuple, C naught plus that R1 is equal to C naught plus D naught, then of course what it does is C naught contains value number 4, D naught contains value number 5, and value number 4 plus 5, it goes and checks at its hash table. it is not present in its hash table, it goes and looks at its parent, and it's also not present in the parent. So that means it has to create a new entry here. So plus 4, 5, it generates a value number 6. So this is 6, this is 4, this is 5. So here what do we do? So 6 is variable R1 contains 6. 6 is present in R1 like this. This is how the table looks like. I'm sorry, this is a bad drawing, but I hope you get the idea. So after processing C, you go to 6 to E. So again, so what E does is it has its own data structure, so it points to its parent. So when it looks for A0 is not present here in its table. It looks at its parent's table, it is not present here, and it goes back to its ancestor, and there it figures out that the value number associated with A0 is 1, and it uses that. And important thing here is once E is processed, you don't go to F because the extended basic block ends here. So you go to the basic block D, and when we go to basic block D, D starts from the D starts from the data structure created by its parent C. Okay, so like for example here, this could be the table associated with E, and when processing D, D will have its own table and it will point here. This could be the table of D. So when D is working, so it first looks at its local table and then it goes to its parent, that is C, and then after it, it goes to the ancestor and it goes and looks at the table associated with D. So this is how this whole computation on an extended basic block works. So the algorithm or the approach that I have described here, I try to explain it, put it in the simplest way so that you get the main idea. You can definitely improve upon it not to get better performance in terms of speed, space, etc. So let's get going. So we want to see one more approach, regional optimization approach, before we conclude today's lecture. So here, the one idea, if you noticed, so when we apply extended basic block approach, when we do value numbering on extended basic blocks, we still lose out on certain optimization opportunities. Like for example, the value A0 plus B0 that is computed here, so we are able to eliminate this redundancy. Let me use this. So this value, we are able to, this is computed A0 plus B0 is computed here, and this redundancy is eliminated. This one will also be eliminated, but this one will not be eliminated because this is not within the scope of the extended basic block. And similarly, this is also not eliminated. But we know that these two are redundant computations. So the next idea is what is called as a dominator-based value numbering approach, which helps us in eliminating these two kinds of redundancies also. The idea here is, if you look at the basic block F, the redundant computation A0 plus B0 here, it can be eliminated by using the value that is computed in basic block C, because in order to reach basic block F, so you have to go through basic block C. That means you have to compute the value A0 plus B0 here. Similarly, in order to get to basic block F, you have to go through basic block A, and in basic block A, we are computing A0 plus B0. So we say these two basic blocks, A and C, they dominate the basic block F. So any computations that are done in basic blocks which dominate F, those computations you can reuse in the basic block F. And the important idea here is since the code is since the IR is in SSA form, we don't need to worry about whether that value gets destroyed in between. So if A0 plus B0 is stored in M0, so this M0 will not be redefined because that is how the SSA IR works. So we can happily use, like for example, V0 is equal to M0 here without any problem. And similarly, if you look at basic block G, so in order to enter basic block G, the only way you can enter basic block G is you have to go through basic block A. You may end up skipping basic block B, or you may end up skipping basic block C depending upon the control flow, but basic block A we cannot skip. Since we cannot skip basic block A, whatever that is computed in basic block A, those computations you can reuse in basic block G. But if you look at basic block F, a computation that is like for example, that the computation, the D doesn't dominate F and E also doesn't dominate F, because you can reach the basic block F via this path or via this path. So if you want to reuse a computation from basic block D, what if the control flow takes the path which contains the basic block? Then you get into trouble. So in the dominator based approach, so we construct what is called as a dominator tree, and we use the dominator tree to guide our redundant computation elimination. So let me kind of give some more intuition about dominators here. So we say that a basic block is dominated. So we say that a basic block B is dominated by basic block A if every path from start node, if you take, there are multiple paths to reach basic block B from the start node. And no matter which path you take, along that path somewhere, you will see the basic block A. So that is, in order to enter basic block B, the only way you can enter basic block B is by going through A. Then we say that A dominates B. In this case, A dominates. And the first observation here is, I'll write down some observations here. The start node all the time dominates any basic block. It doesn't matter what basic block. The start or entry basic block. We are using the notation entry basic block. So let's use that. So the entry basic block all the time dominates the basic block A, number one. Number two is every basic block dominates itself. So these are the two kind of base cases you have. And the second important thing is, if basic block, let's say, if basic block B dominates C and basic block D dominates C, then there should be a relationship between B and D. Either B dominates D or C dominates D. Right? So why is it? Let's see, why is this? So what we are saying is, let's consider the case. So we have that basic block B dominates C and basic block D dominates C. So if basic block B dominates C, then starting from entry node, okay, no matter which path you take, the basic block B should be present here. So similarly, so since D dominates C, in any path you take, D should also be present here. So it has to be the case, if you think about it a bit, let's say if there is no relationship between B and D, right? So then that means there exists a path in which you can reach D, you can reach C without going through, in which B is not present, in which B is not present. Immediately it implies that B doesn't dominate C. So I think in order to cut the long story short, what I would say is if B dominates C and D dominates C, it has to be the case there should be some kind of relationship between B and D. Either B dominates D or or D dominates B. So let's try to understand this with the help of an example so that we can become easy. So if you see this example, I'll just take 5 more minutes and conclude this lecture. So if you see, let's start with this control flow graph. We start with A. From A, we can immediately see that A dominates B. Okay, so we are constructing what is called as a dominator tree now. A dominates B. And then you can also see that A dominates C. Okay, because if you want to get to C, the only way you can get to C is through A. And we can also see A dominates G, because in order to get to G, the only way you can get to G is through A. And F cannot dominate G because you can bypass F and take this path and reach G. Similarly, D cannot dominate G because there are paths which lead to G without going through D. So similarly, the case with E and C. So only the node A dominates G. And if you look at the basic block D, D is dominated by C and it is also dominated by A. Similarly, if you look at E, E is dominated by C and it is also dominated by E. And you look at F, F is not dominated by D or E because either you can take this path to reach F or you can take this path to reach F. But it is definitely dominated by C. So what we can do is we can take a control flow graph and construct this dominator tree. And from this dominator tree, we can say, given a basic block, what is its immediate dominator? So like for example, the immediate dominator for D is its parent in its dominator tree, which is C. Similarly, the immediate dominator for G is its parent in this dominator tree, which is A. Similarly, the immediate dominator for F is C, is the basic block C, which is its parent in this dominator tree. So what we can do is we take the control flow graph and we construct this dominator tree, and from the dominator tree we can identify what is the immediate dominator associated with a basic block. And this dominator tree is helpful in many optimizations that we perform in compilers, including construction of SSA and finding loops in your control flow graph, so on and so forth. So how do we use this dominator tree in our local value numbering approach? So the idea is very simple. So we start with this dominator tree and traverse this dominator tree in a DFS fashion. We know that there is a data structure associated with A when we are performing local value numbering on the basic block A, which consists of variable to value number map, value number to variable map, and hash table. And then when we do a DFS on this dominator tree, you go to basic block B, and then you construct the local data structure, and similar to super value local numbering, you make this point to its parent. So when you are trying to eliminate redundancies, you first check your table locally, and if you are not successful, go to your parent and try to use the computations that are there in the parent in order to eliminate computations locally. Similarly, so this is the table associated with basic block A, this is the table associated with B, with A, this is with B. And when after we process basic block B, you go to basic block C, and then you construct a table for it, which is TC, and with this also points to its parent. And then similarly, after that, you go to the basic block D, the table associated with it is TD, and then this points to D. So when we are working with D, you check locally whether if you can eliminate computations with the help of the table locally. Otherwise, you go to its parent, which is the basic block C. Otherwise, you go to the, and if you are not successful here, you go to its parent, which is the basic block E. That's all. So this is how we can make use of for the dominator tree in order to eliminate redundant computations at a region described by, induced by this dominator. An interesting idea is this region is not a continuous region, because in the case of extended basic blocks, you can see A, B, C, D, E, it's a continuous region. But if you see this the region induced by dominator tree, while processing G, we are considering the basic block A in order to check if there are any redundant computations which it can eliminate. So I will conclude my lecture here. So this is all about regional optimizations. I hope you are able to appreciate the nice ideas that modern compilers use in order to optimize the IRs. So we have looked at how to do optimizations at a basic block level, and then we have seen how we can extend it to work at a super value at an extended basic block level. And then we have also seen how we can apply it at the level of regions induced by dominators. In the next sessions, we will see how to work at the whole control flow graph level, that is at a per function. So that's all I have for today. Thank you. If you have any questions, you can ask me.